So this is my presentation for Project 2, Signal Noise Analysis and Reduction. This project focuses on digital signal processing, specifically noise analysis and reduction in audio signals. Objectives included reading and writing original and noisy audio files, analyzing noise characteristics, creating custom noisy signals, and applying various noise reduction techniques to reconstruct the original audio as accurately as possible. Effectiveness of different filtering approaches was evaluated using signal-to-noise ratio and mean squared error. Analysis began with loading the audio files and performing basic waveform visualization. I confirmed that the sampling rates were consistent across files to ensure accurate comparisons. However, the sizes of the signals were different, which caused some confusion later in the project. The time domain representation provided initial insights into signal amplitudes and potential noise patterns. Signals were converted into the frequency domain via the fast Fourier transform, which returns a discrete Fourier series. This allowed me to observe how energy was distributed across frequencies. After computing the FFT, I identified the frequency range where the signal and noise components were most prominent, centered on 1730.4 Hz. Isolating this noise component was achieved by subtracting the clean signal from the noisy one. I implemented and evaluated 3 filtering approaches. The notch filter, which is designed specifically to remove the dominant noise frequency. The filter bandwidth was automatically calculated based on the decibel points of the noise spectrum. The bandpass filter was implemented to preserve signal frequencies between 100 and 8,000 Hz, while attenuating frequencies outside this range. Spectral subtraction used the isolated noise spectrum to directly subtract noise components from the noisy signal while preserving phase information. The next portion of the project focused on creating custom noise and adding it to the original signal. I generated uniform random noise with a controlled amplitude taken from the noise profile in Part 1. This simulated electronic interference with equal energy across all frequencies and proved challenging to filter out. I also created pink noise to simulate more realistic environmental conditions. Although my research indicated that pink noise is related to Gaussian noise with a frequency response of 1/t, MatLab Sound Library has a built-in pink noise function, which is quicker and more accurate than a custom implementation. Pink noise contains higher energy at lower frequencies, mimicking many real-world acoustic environments. All outcomes were evaluated using signal-to-noise ratio and mean squared error metrics. Signal-to-noise ratio compares the power of the original signal to the power of the noise. In signal processing, a higher SNR means the signal is more dominant than the noise, indicating better clarity and more effective noise reduction. Mean squared error measures the average of the squares of the differences between the original and reconstructed signal values. The notch filter proved most effective for this particular noise value, achieving the highest SNR and lowest MSE values. This makes sense given that the noise was concentrated at a specific frequency. The filtered audio was saved as reconstructed audio.wave, and this was the best filter for the original noisy signal with minimal impact on signal quality. Bandpass filtering offered moderate performance for the main test signal, improving SNR while preserving most signal characteristics. Spectral filtering also proved effective. However, it was slightly performed by the notch filter, which had a slightly smaller MSE and higher SNR. For uniform random noise, I used the Wiener filter, which provided consistent noise reduction across frequencies. However, it resulted in noticeable signal distortion. High-pass filtering used for filtering pink noise proved moderately effective. However, there is still noticeable signal distortion. Several technical challenges emerged during implementation, including signal length matching, filter parameter selection, and time considerations. For signal length matching, differences in signal length complicated direct comparisons and subtractions. This issue was resolved by resampling the signals to ensure consistent lengths. For filter parameter selection, determining optimal cutoff frequencies and filter orders required iterative testing. This process was time-consuming raised the question of real-time processing trade-offs. How valuable is the output compared to the time required to process the signal? Lastly, an important consideration throughout this project was the distinction between ideal and real filters. Ideal filters have perfect characteristics with infinitely sharp transitions, perfectly flat frequency responses in the passband, and infinite attenuation in stop bands. However, real-world implementations face limitations, including causality requirements, finite order constraints, and computational complexity trade-offs. In this project, I use techniques like zero-phase filtering with filter-filter to mitigate phase distortion, an approach possible for offline processing but not in real-time applications. These practical constraints highlight why filter design must balance theoretical ideals with implementation realities. Future work could explore adaptive filtering techniques that automatically adjust parameters in response to changing noise conditions, as well as machine learning approaches capable of distinguishing signal from noise. The code for this file, I found it was easier to present it as an MLX file, and it could be run by sections rather than trying to rerun the entire file every single time. So here you can see part 1, task 1, we load and visualize the audio files. We also create time vectors for plotting, and as you can see, the noisy ice cream.wave was actually the clean signal, and ice cream.wave was the original signal. From there, we do task 2, frequency domain analysis, plot spectrums of the clean and noisy signals. Move on to noise characterization, find the mean and the variance. We also show the clean signal, the noisy signal, and the isolated noise. Spectral analysis, we can see the noise spectrum frequency, and here we can see that the dominant noise frequency is 1730 Hertz. For noise reduction, we first implement a notch filter, followed by a bandpass filter, and spectral subtraction. Also, something that I found was important was normalizing the filtered signals to match the original volume of the signal, which cured some of the problems based on my own judgment rather than on metrics. Moving on, you can see the filtered signal profiles. The notch filtered signal removed the noise entirely, but it also produced some distortion. Bandpass filtered signal produced less distortion, but did not remove as much noise. And the spectral subtraction, like the notch filtered signal, removed the noise, included some distortion, but ultimately it was just outperformed by the notch signal. Part 2, the creation and removal of custom noise. We display the original clean signal, the uniform random noise, and the signal with the uniform random noise added. For pink noise, we use MatLab's pink noise signal, and you can see the original signal, the pink noise, and the signal with pink noise added. Task 2, we create a filter for the uniform and pink noise, plot the results, and compare the outputs. As you can see, the pink noise and uniform noise were not as successfully filtered as the original audio. However, the SNR improvements are noticeable.